Thanks for coming to our learning series this evening, everyone. I'm happy to introduce Dr. Wes Ryle. He's the astronomer for the Cincinnati Observatory, a historic observatory that focuses on public outreach and science education. He was formerly a professor of physics and astronomy at the Thomas More University and director of their campus observatory. During this time, he led many undergraduate observational astronomy research projects, focusing on topics such as eclipsing binaries, transiting exoplanets, and cataclysmic variables. I have no idea what those are, but I'm excited to learn more. So take it away.
All right. So thank you so much for having me, Tracy. This presentation is based a little bit off of a class that I gave at the Cincinnati Observatory on light pollution a few months ago. Some of the folks here were actually there in attendance for that one. And it's also in partnership and based off of a presentation that my friend from grad school, Dr. Stephen Williams, gave to the Friends of the Observatory group. That was probably about a year ago now. And he's based in Flagstaff, Arizona, with the U.S. Naval Observatory. And so he's done a lot of work with maintaining the dark skies out there. If you're, familiar with, the Dark Sky Initiative, then Flagstaff is kind of world renowned in terms of being a dark sky friendly city. And so there are some slides in here that I borrowed from him. He's on the call. I asked him to join just to keep me honest. And I told him that if anybody has any really tough questions, then I'm just going to send them to him. And I've also recommended, for Tracy that maybe at some point in the future, if Dark Sky Ohio wanted to have him to give a little bit more detail on kind of how Flagstaff tackles this, it's a really good, example to go off of. So we're going to talk about how artificial light, how light pollution affects kind of professional astronomers. I know that you've probably had a lot of presentations on all the wide range of effects that light pollution can have, but we're going to try to focus in on those specific issues that are related to doing professional astronomy. The talk I'll have just a real quick recap of light pollution and how those effects are kind of worsening over time. Talk a little bit about how light has encroached on the majority of professional observatories in the world. The actual direct effects on astronomical observations, and then a little bit on how Flagstaff tries to deal with this problem, in terms of interacting with the community, interaction between the community and the observatories that are there. And then we'll talk a little bit about the other type of light pollution problem, which is not necessarily as easy to tackle. Any guesses on what the other light pollution problem is for astronomers? Satellites, right? And so it's still really a form of light pollution, but obviously it very much impacts astronomical observations, whether you're talking about professional or amateur astronomers taking astrophotography. It's a huge problem and kind of gets lumped into this kind of discussion quite a bit, and so I thought it was worthwhile mentioning. So a couple of slides here at the beginning that have just some more recent publications related to the effects of light pollution, how they've been changing over time. This is available via Globe at Night because that's a group that actually does measurements of sky brightness worldwide. And it mentions here that from 2011 to 2022, about 51,000 citizen science observations of night sky brightness showed that the a number of visible stars was decreasing by amount that can be explained by an increase in sky brightness from 7 to 10% per year. And this was actually higher than what was kind of expected based on some estimates, just based on the growth of lighting worldwide. And so it gives you an idea of how quickly the problem is increasing over time. This is also another article that's talking about just how widespread of a problem it is. So this group from Colorado shows that 80% of the world, or more than 99% of US and European populations, live under light polluted skies, and the Milky Way is hidden from 1/3 of humanity. And it's worse for North Americans than it is for Europeans, for example, but still bad for the majority of folks that are out there. Of course, you've all seen light pollution maps like this. These are updated pretty regularly. and based on satellite data. And you can always see that, in general, the eastern half of the U.S. is worse off than the western half of the U.S. And zooming in on our region a little bit, you can see that, at least for me at Cincinnati, it's hard to kind of go in any direction to escape the light pollution. Whenever people ask me at the observatory, where can I go to see dark skies? Of course, we mention places like Stone Lick State Park or Caesar Creek or Hocking Hills as examples. But really, you need to travel pretty far to the east of Cincinnati, and that's really the only direction that you can go in order to have any chance of seeing a dark sky. And this is also a simulated view, kind of showing how things have progressed from the 1950s up until about 2025, and just showing how rapidly, again, a problem it really is. These are all things that you've probably heard of, along with kind of the widespread effects of white light pollution. Again, we're not going to focus on all these different effects. I'm going to focus in on just the astronomical aspects. But from previous meetings or from literature or whatever you might have, you know that there's a wide range of effects. But of course, a lot of astronomers would probably say that we've been trying to address this problem for a long, long, long time, just because for the majority of history, at least after the development of electricity, we've just gradually had to deal with this problem more and more as time has gone by. And it's especially a problem, for someplace like Cincinnati Observatory, which kind of it's one of the first observatories in the US. The original observatory was built literally on a hillside looking over downtown Cincinnati. It was on Mount Adams, which literally just has a view of downtown. And this was, of course, before the widespread use of electricity. But interestingly enough, for Cincinnati, it was built in 1843. The observatory was. The telescope was first used in 1845. And then within a decade, actual physical pollution, right? Coal smoke was being produced so thickly in downtown Cincinnati that astronomical observations became impossible. So they moved the observatory out a few miles out to the east in a very rural location, and to get away from that smog. But now today, even though we moved away from the city, we're still very, very, very light polluted. And so um, the observatory's research kind of arm in terms of actually making observations, astronomical observations, that pretty much ended as early as the early 1900s, just because of the light pollution. And so that made us switch to become an outreach and education facility. And you actually see that happening for a lot of different other institutions across the world too. This is kind of an extreme case. This is Mount Wilson Observatory. If you've ever been, it's a beautiful site up on the hills, and um, technically mountains above the LA basin. But this is showing from the Mount Wilson Observatory looking back towards LA, the view in 1910 versus 1925 versus 2002, how that basin, basically filled, and obviously is a very light polluted area now. There's still research facilities on Mount Wilson, the place where I went to grad school, along with Dr. Stephen Williams. Georgia State University has a facility out on Mount Wilson. And so it is still possible to do research out there, but the light definitely is encroaching on that area. This is a graphic that I found from a study in 2023 that's showing sky brightness above natural background levels along the kind of x-axis down there, and the different observatories, major different professional observatories around the world. And so you can see some of the classic ones, some of the ones that made huge contributions to astronomy back early on, like Lick Observatory or Palomar. Those are now in a situation where they are incredibly light polluted, and harder to do astronomical observations from those locations. In general, the majority of the U.S. sites, the continental U.S. sites, have become pretty light polluted. Kitt Peak, as the national observatory location, was once a very nice dark sky site, but Tucson has been expanding, and so you see it kind of middle of the list here now. And then if you go all the way up to the top, you notice that the top three there are Chile. locations. And so, there's been a huge expansion of observatories that have been built in Chile, partly to exploit the southern sky, but also to exploit these very, very dark locations kind of in the foothills of the Andes or in the Atacama Desert. And very much related to that, you all were just mentioning the um, data center project that got canceled here in the area. There was a lot of worry and a lot of articles that you saw coming up about the best site basically on this list down there in Chile, down in the Atacama Desert. And there was this industrial mega project that was being planned to be built basically within sight line of this observatory. And so there was a bit of an outcry in terms of trying to preserve that dark sky location. There was a lot of money being invested in these observatories, these telescopes being built specifically at this location for their dark skies. And the industrial mega project, it was actually a green project. They were wanting to build a solar farm and wind farm there in the Atacama Desert, which, if you can imagine, the same thing that makes it good for an observatory, clear skies and dry conditions, also makes it good for solar energy and wind energy. But fortunately, just within the past month, there's been word that they have abandoned that project down there in Chile. It's not, I don't think it's completely official yet, but they have indicated their intention to stop that project. And so this is still definitely an active battle. And something that's taken place for observatories around the world. Now, in terms of how it actually affects astronomical observations, and this is true whether you're doing amateur astrophotography or whether you're doing professional astronomy, the biggest contributor is sky glow, right? The same thing that makes it just not possible to view the majority of the stars in the night sky, sorry, is the same thing that affects our observations. On the left is some images from Celestron's website. To be fair, I think these images probably are just them adjusting the contrast and brightness on a single picture just to kind of show the effect. But on the right is a more realistic representation. This is the Pleiades star cluster. And one was taken at I forget the Bortle number for the two different locations, but one on the left is obviously a very light polluted area, and the other one was a dark sky site. And so you can see the relative difference in just the background sky glow. And of course, that just decreases your contrast in terms of what you can actually see. Obviously, it affects the visual appearance of the picture. But what's important for astronomers is that when you're making measurements, the most important thing for you is your signal to noise. And so some of you have probably heard this before. Again, it's something that's used for either amateur astronomy or for professional astronomy. But when you're trying to detect a source, whether it's a star or a galaxy, whatever it might be, you're wanting to get the signal, the light from that source to be high compared to the background noise. And that background noise comes from a few different sources. Some of it is related to the camera itself, but the majority of that noise is related to the light in the sky noise. And so this graph over here is showing, say, for a single image that you might be taking, how the different types of noise increase as you increase the exposure time. So as you increase the amount of time that the camera shutter is open, and how the signal of the actual object changes. And so in the kind of middle of the graph, the solid black line is the signal, which increases roughly linearly with exposure time. So if you double the exposure time, you're getting twice the signal from your object. But you can see that the biggest contributor here is this blue dashed line, which corresponds to sky noise. And it's also increasing with exposure time. And so if you're in a site where sky noise is high, where the sky brightness is high, then you're going to be in trouble, especially if you're relying on single images. And amateur astronomers or professional astronomers know that you can also sometimes stack images, but that's going to require more telescope time, and it still has its limits in terms of improving the signals to noise. With astronomers, the thing that you always have to keep in mind is that Time is literally money, right? We have lots of these big professional observatories, but they're usually overprescribed in terms of the missions and the projects that they are carrying out. And so astronomers can usually apply for time at different facilities, and then their proposal gets judged against others. And so you have to make the case that your use of the telescope is worthwhile. And so when you have to combat that with increased exposure times or increased number of images, you're obviously you're in a situation where the time is not available for everyone. Now, the other thing that we know, and this is true again for how it affects the human eye, but also how it affects imaging, is that the color of the light matters. And the thing that often comes up in these discussions is that, the reason that our sky is blue is because of Rayleigh scattering, where blue light is more susceptible to scattering in our atmosphere than red light. And so that blue light from the sun has a tendency to get spread out over the atmosphere, which causes the blue appearance of the sky. But this is also true for any light source on the ground, right? So if you have a light source on the ground that has a higher concentration of blue light, that light is going to get scattered over the atmosphere, and more so than the red. And this has been a big problem because LEDs, while they are very energy efficient, and in that sense, they're definitely a good replacement for things like incandescent light bulbs, LEDs also have a tendency to be bluer in light. And so the widespread use of LEDs for outdoor lighting has led to a even worse problem as far as sky glow goes, because that blue light has a tendency to spread more through the atmosphere. Just real quick, in case we've got folks on the call that aren't as well versed in what we mean by a spectrum. So when we talk about different colors of light, sometimes it's useful to refer to a spectrum or plural spectra. It's of course what you get if you take light and you either pass it through a prism or you pass it through a grating so that it spreads out into the rainbow of colors. It's the same effect that creates the rainbow that you might see during a rainstorm. In astronomy, we do this all the time where we collect light through a telescope, we pass it through a slit, we pass it through a prism or a grating, and we get that spectrum. And that spectrum has a tendency to show features inside of it. Sometimes they might appear as dark lines on a kind of rainbow background. Other times they might be bright lines on a dark background. But those lines contain a huge wealth of information for astronomers. Even if an object is halfway across the observable universe, if you get a detailed spectra from it, you can tell what it's made out of. You can tell something about its motion. You can tell something about its rotation. And you can even get even more detailed information about pressure conditions or density conditions or temperatures. And so there's a huge wealth of information in spectra. For the purposes of talking about some graphs that we're going to see here in just a second, right? If you think of a spectrum as a rainbow with dark lines on it, like this picture that's kind of at the top of the right-hand side picture, that's what a picture of a spectrum actually looks like. But when scientists are actually investigating spectra, they almost always look at it as a graph. And so the graph of a spectrum is always brightness or the intensity of the light on the y-axis, and then wavelength or color along the x-axis. And so wherever there's dark lines in the picture, that corresponds to dips in the graph, dips in the spectrum. And so you almost always see it as a graphical representation just because it's a little bit easier to extract information from that. I've got a statement down there that spectroscopy, I think most people, most astronomers would consider it to be the most lucrative form of observation that you can have. But it's also costly in terms of resources. You need bigger telescopes and longer exposure times, basically because you're spreading out the light, right? And so if you want higher signal to noise, the fact that you're spreading out the light automatically means that you're going to need higher exposure times. You're going to need larger telescopes to collect more light. And for all the reasons that we've talked about so far, that also makes spectroscopy highly susceptible to the effects of light pollution. The other thing that we do in astronomy when we're taking images, in particular when we're measuring the brightness of an object, we try to use standardized filters so that we can share data in between observatories and between telescopes, and it's apples to apples and oranges to oranges. As you might expect, if you just slap a camera on any given telescope, that camera and that telescope and that site are all going to have slightly different responses. And so by creating these standardized filters that are commonly used in observatories around the world, we can calibrate the data and then share it, and it'll all be on the same scaling, basically. There's lots of different filter sets that exist out there. One of the ones that has been around for a very long time is the Johnson-Bessel UBVRI system. And this is showing the graph similar to what I was talking about before, where visible light, if we go back here, goes from about 400 nanometers up to about 700 nanometers. And so on this graph, the visible range is right kind of in the middle. And you can see the B filter, the V filter, and the R filter are typical ones that we use for astronomy when we're taking measurements of brightness. That science is called photometry, the measurement of light. And so in particular, with the LED kind of explosion that's happened, observations in B and V have a tendency to be a little bit more affected by light pollution in the LED age. And this can even cause problems just because the nature of the night sky has changed over time. And so our ability to collect in filters, in different filters, has changed over time. And the efficiency of those different filters has changed over time. So this is showing the spectra of different types of light bulbs that are out there. And so this is 9 different ones. And so there's a lot of different acronyms here. But some of these we're going to look at in a little bit more detail here in just a second. LPS stands for low pressure sodium, and HPS stands for high pressure sodium. And so those are some older traditional lights, outdoor lighting, especially for places that are dark sky friendly. NBA LED stands for narrow band amber LED. PCA is a phosphor converted amber. The F in front of the LED is indicating it's a filtered LED, and then warm white or cool white, those terms that you might see. And then down here at the bottom are different LEDs that have just that color correlated temperature. You'll see it as a temperature listing on the bulb itself. And what I want you to notice here is that in general, for astronomy, narrower spectra of the light is better because then you're only interfering with a very narrow portion of the entire spectrum of whatever object you might be taking. And in general, redder is better just because the response of the machines and in terms of the spread of the light through the atmosphere that we were talking about before, the sky glow effect. And so low pressure sodium are still very wonderful lights for outdoor lighting. But we can see one of the newer alternatives is this narrow band amber that functions pretty similar to the low pressure sodium and has been a popular option. We'll see here in a second that high pressure sodium is can be replaced with the phosphor converted amber and kind of produce the same type of light, but with less leakage into the blue. But in general, all of these LEDs have a higher blue contribution than any of these other options, and so tend to be worse for astronomical observations. The other thing you can also look at is how the different types of light affect sky glow, affect sky brightness as you go farther and farther away from wherever it is you are. These are all scaled to high pressure sodium, which is why high pressure sodium is just 1 right there on both of these graphs. But it's basically showing that here in the bluer portion of the spectrum, so 350 to 500 nanometers, again, the LEDs are very, very bad, especially even out to very large distances in terms of sky glow. And then the redder portion of the spectrum, you can see the LEDs perform a little bit better because they're in the bluer part of the spectrum. But still, low pressure sodium and some of the other options that we talk about still perform very well in either situation. So real quick, and again, Steve's on the call, so if you have questions about kind of what Flagstaff has done, it's sometimes referred to as the Flagstaff solution. I'll give some websites at the end that talk about what they mean by the Flagstaff solution. But it is a great collaboration between the community and the observatories that are out there. It's known as the world's first international dark sky city, and it's because of that connection between Flagstaff and Lowell, the fact that they grew together, that really made this something that stuck and has worked over time. This is a image that shows two similar sized cities. So up on the top, you see Cheyenne, Wyoming, in the middle, and then down at the bottom, you see Flagstaff, Arizona. And this is just kind of showing you the sky glow that's produced by those two towns. And what you notice, these are both roughly the same distance away from equal population towns. And you can see the huge difference in sky glow that's created by those cities. You can be in downtown Flagstaff on a moonless night and actually see the Milky Way, which is pretty impressive for a city of that size. You can also see here that in this image, Flagstaff sky glow and Phoenix's sky glow are almost identical, despite the fact that the location of this image, Phoenix is about 5 times further away. And so that, and of course, is a much, much, much larger city than Flagstaff. So those light sources that we talked about before, these are all ones that Dr. Williams has dealt with out there in Flagstaff. High pressure sodium and low pressure sodium were the kind of go-tos for a very long time, but we're starting to see a little bit of a transfer over to the phosphor converted amber, the PCA, and the NBA, the narrow band amber as well. Phosphor converted amber has a layer of phosphor around the blue LED chip, which kind of filters the light and produces that orange or amber glow. And he often is out on the streets of Flagstaff trying to make sure that lightning enforcement code is being followed. And so this is a picture that he took at an intersection. And you can see that even at this intersection, there are a wide variety of lighting fixtures that are using different types of bulbs. And he has a little handheld spectroscope that he can go around and measure the spectrum. And in this case, you can see this bulb down here that has the orangish glow. This is one of those narrow band amber, whereas this is an LED. And so you can see the bright blue bump on the LED. And both in the picture, right, you can visibly see that this is much brighter, has much more glare. But then also in terms of the spectra, you can see the huge difference in the bulbs there. You also can get detailed measurements in terms of the impact that it has on sky glow, and how much of the light is coming out at blue versus other wavelengths. If you just look at the sky glow impact as the kind of main indicator, you can see that the LED has a value of 5.6 and the NBA has a value of 1.29 here. And so many multiples times worse in terms of the sky glow for the LED. This is another intersection. In this case, no LEDs here, which is good, but it's comparing high pressure sodium there in the distance to a phosphor converted amber there in the near side of the image. And so you can see again very similar in terms of their spectra, but the high pressure sodium does have a little bit of a bump there in the blue, which makes the phosphor converted amber just a little bit better for astronomical studies. This is kind of showing a direct comparison. I can just flip between the two. A lot of times HP, the high pressure sodium and the phosphor converted amber are kind of seen as interchangeable. And you can see that they are pretty well matched in terms of the overall color of the light. But again, the PCA is just getting rid of the blue bump there that makes it a little bit more accommodating. And then this is low pressure sodium compared to the narrowband amber. And you can see that narrowband amber is a little bit wider than low pressure sodium, but still very comparable in terms of the light that it puts out. And so in terms of a big picture, this kind of shows over there on the right the relative visual sky glow impact kind of on a scale there of these different light sources. And you can see that in general, any kind of LED, correlated temperature LED, is going to be much, much worse than these other types of lights. HPS can be replaced by PCA with a slight improvement. Technically, low pressure sodium is still the winner in terms of all of these, but narrowband amber is performing just as well. And these different types of lights, if you try to, do a search for phosphor converted amber bulb or a narrowband amber bulb, they're not necessarily easily accessible by individuals yet. That's hopefully coming in the future. But if you were talking to a municipality or you were talking to somebody who was going to put in a big project, these are all terms that would be known by those companies in terms of the lighting, the outdoor lighting that they're going to put in the facility. And so these are things that are available on those kind of corporate commercial level or whatever you want to call it, quite large scale, but not necessarily for the individual consumer just yet. And then just real quick, the other light problem, if you're an astrophotographer or professional astronomer, you know this is something that happens very regularly. I've been doing astronomy for about 20 years, and I experienced the fact that, when I was doing this as a college student, you might get a satellite streak across your image maybe 5 times a night. And nowadays, when you try to go and sit and take a night's worth of data, it's every other image that has a satellite streak through it. This is an example of an image taken by one of the larger scopes down there in Cerro Chile, shortly after one of those Starlink launches, where again, there's like 24 satellites or more that are kind of going in a line across the sky. The scary thing is that it's already bad in terms of the Starlink satellites that are up there. I think the total satellite count right now is around 14,000. This graphic over here on the right has 2024 at about 10,000. That's already increased up to 14,000. And Starlink is just the beginning, right? So there's lots of other corporations that want to put their own communication satellite constellations into orbit. And there's even a proposal, I think, from Starlink right now to do a million satellite constellation with a million satellites that is being reviewed currently. And so down there in the lower right, you see that there are 1.23 million proposed satellite projects in various stages of development at the moment. Um, this is a problem for astronomers. It's also a problem in terms of security, just having too many satellites up there. And you might have heard about things about how you can have a cascade failure if anything goes wrong in terms of satellite debris causing other satellites to be disrupted and going, it's called the Kessler effect. And so it's definitely a problem for astronomers. And we should never leave out our radio astronomer friends as well, because when you're talking about Earth-based observations, it's really visible light telescopes and radio telescopes that can do the majority of the work. And radio astronomy deals with noise as well, deals with light pollution, if you want to call it that way as well. So for example, if you ever get a chance to go to the middle of nowhere in West Virginia, there's a beautiful gigantic telescope out there called the Green Bank Telescope. This picture doesn't do it justice because that dish is a football field wide. Um, but the reason that it's in the middle of nowhere is because it's very intentionally placed inside this national radio quiet zone, where there's very strong restrictions on having radio sources. And so that could be a malfunctioning microwave. It could be, somebody, you're actually, for a long time, you weren't allowed to use cell phones anywhere near the Green Bank Observatory. And so they deal with these same kind of problems. It's just a slightly different effect. And the Starlinks even affect those as well because those Starlinks are leaking radio signals. And there are some radio signals that are supposed to be restricted based on astronomy use. And they're finding that the Starlinks are also leaking at some of those restricted frequencies as well. And so it's a problem not just for visual, but for also radio astronomers as well. So just a few resources. Lots of these are probably things that you might have looked at before, but if you wanted to look a little bit more in detail about what Flagstaff is doing, there's some sites that are related there. And I'm putting my friend Dr. Williams on the hook here. I've got his email address there. He's getting more and more into dark sky and battling light pollution with his role out there at the U.S. Naval Observatory. And so he's helped me get into this as well. And so I've got his information up there just in case you're wanting to contact him as well. Thank you all so much.
Um, Thank you so much, Dr. West. That was a great presentation. So many good, helpful facts. And, I think a lot of us have been fighting light pollution for a really long time, but I think some of those graphs really cemented it in my mind a lot better. So,
Hmm.
that was very helpful. So thank you. My first question was, can we borrow any of your slides if we wanted to?
So yeah, I checked with Dr. Williams because I was really worried at first because some of his slides obviously are coming from a government a military organization. And at least last time I got his approval to share these slides. And so as long as he says it's okay now, that's still true, Steve?
Hi. Yes. The process for any talk that I am required to give is that it has to pass several checks. Content, technical, and then a security review. And so everything that Dr. Ryle has shown here has gone through all of those. It's passed through our public affairs office, and even our public affairs officer uses a lot of these slides too. So feel free, just as you noticed how Dr. Ryle cited the individuals like Dr. Mark Murison for that original photograph. If you could
Mhm.
just do that, that's all we could really ask.
Okay. I'm going to pass along to the rest of the group. Do we have any individual questions right now? I had a couple more questions.
Hmm.
Um, I'm assuming everybody kind of understands the Bortle scale is kind of when we talk to communities, ideally is a 1, terrible is 9. As far as in Ohio or in the Midwest, what do you think is a maximum Bortle that we could aspire to in these areas that would make it easier to see and use telescopes and use observatories? Like if Cincinnati could get down to 4 or 5, what would be reasonable for, some of these more metropolitan areas, would you think?
Hmm. So it's hard to give like a blanket answer because it kind of depends on which type of study you might be doing. For example, I spent 16 years at Thomas More University, and obviously that is an incredibly light polluted site, just as bad, if not worse, as the Cincinnati Observatory. And if you're doing studies that just rely on um, measuring brightness changes, and it's called differential photometry, that's where you're measuring the brightness of a star or a planet or a galaxy or whatever it might be, and you're comparing its brightness to other objects that are in the same picture, right? If you're doing that, where the effects of the sky and everything else are happening equally across that single picture, then you can still do science and you can still do research. It's only when you start to get beyond that, when you start to think about either kind of more calibrated forms of photometry, calibrated forms of brightness measurement, or if you start talking about spectroscopy or things like that, where you really, really become limited. And so you can do differential photometry from light polluted skies. If you wanted to do more intense observations, again, it's hard to give a blanket number because it would depend on the brightness of the objects that you're wanting to study. Obviously, the more light polluted the skies, the more you're limiting yourself in terms of the objects that you can actually achieve with any given telescope.
Um, Next question. The narrow band amber.
Mhm.
Um, I don't know if I see that a lot when I'm looking, when I'm recommending different light fixtures
Mhm.
to folks. Do you know offhand if there's a cost difference between that and, we'll say the warmer LEDs at this point?
Um, Steve, can I go to you?
Absolutely. Yeah, I Dr. Ryle touched on it a little bit. This is part of the cutting edge of the lighting industry currently. Um, Developing the LEDs is one thing, but then coating them with some sort of material, typically phosphor, to give a more broadband um, emission, so you get more of a white light. Um, that is easier to do and cheaper to do. And so when you want to really cut down the light, it does cost quite a bit more. And those narrowband amber fixtures are typically quite expensive compared to um, the white light color correlated temperature type of LEDs. Um, at least twice as expensive. Even if you find bulbs, and you'll sometimes find them on lighting websites or on Amazon, and they'll be labeled turtle friendly, right? For the turtle hatching, for example, down in Florida on the beaches, you can sometimes find bulbs there, and those are typically the equivalent or close to narrowband amber or phosphor converted amber. And even those, for example, I purchased one for kind of a public outreach example, kind of a show to show the differences between lights. And one of those bulbs, which I've seen around town at retailers, Target, that kind of stuff, they'll have a phosphor converted amber outside of the entryway to their store. Unfortunately, right now, those are as much as 10 times more expensive than the equivalent LED bulbs. And sometimes it's very, I'm preaching to the choir, getting people to budge on that who have limited budgets. It's just not going to happen, unfortunately.
Wow. Well, maybe as time goes on, the cost will come down. We can only hope, I guess. Wow.
Yeah, that is one of the things that's very nice. A lot of the metrics that the lighting industry use or municipalities use when they're installing these lights are things like, you know, um, how much light do I get per watt of power that I give it, and um, the the amber lights, whether it's phosphor converted amber or narrowband amber, are getting better all the time. But so many municipalities have already gone to white light
Mhm.
LEDs. They're not going to spend 5 times, 10 times as much to get different bulbs. So we could only hope to change their mind going forward when they start to have to replace those lights for whatever reason.
Right. I'm gonna ask you another question, Dr. Williams. Um, what have you found to be successful in Flagstaff to maintain your dark skies as far as messaging so that we can kind of take what you've learned and transition that into Ohio? What has been successful as far as your messaging? I think one of the things that we have issues with is obviously crime. Can you say anything about that right now? If you can compare, we hear that if we don't leave our front porch lights on, then, that's how criminals are going to get us. Can you say anything about that?
Sure, I can kind of give a short version. Um, as far as I know, criminals still need to see to open a door or hack a lock, this kind of stuff. One of the best methods that we kind of put forward are motion sensor lights, and those will get tricky as well. In Flagstaff, when a deer runs by, your light turns on, your heart rate goes up. What's going on? Oh, it was a deer that's staring back at me in the dark. As of now, and I am very open to any kind of suggestion for research studies, in-depth analyses, etc., etc. There has been no correlation that um, if you light something to a certain level with either white light versus amber light, that there is a difference in crime. It gets really kind of strange. Just very quickly, one of the studies that I saw was done in New York City, and they used diesel powered white LED lights that are sometimes used for construction at night. You've seen this on the roads in different
Mhm.
places. And they put those around, had to refill them with diesel gas every day. And what do you know? Crime was less around those for some strange reason. Might have been something other than just the light. So I haven't seen anything on that that has been definitive in any way, shape, or form, and that usually, um, that kind of stops the conversation, whether fortunately or unfortunately. As far as the successes in Flagstaff, I could give an entire talk on it, but one of the primary things is that just like with new construction, you have different codes that you need to follow: plumbing codes, electrical codes. We have a lighting code, and you won't be able to open your business if you don't meet the lighting code or if you don't meet the electrical code. And so that gets enforced at the municipality level. Um, Grandfathered in stuff eventually has to be replaced, and it has to follow the code. Flagstaff has had a long history. Dr. Ryle talked about it. Um, Collaborations from the Naval Observatory and Lowell Observatory, and just the general tenor and attitude of the whole place is very much in favor of dark skies. It was kind of um, heralded as an astrotourism place. Come see the dark skies. It's an appropriate slide that Dr. Ryle has up now. Where do I go to find really dark skies? That kind of thing. So, even in the Chamber of Commerce, the city council, even business people, no, we want, hotel chains. We want people to come here because we have the dark skies. Yes, we'll put in those amber lights. So it's kind of a serendipitous confluence of a lot of different things.
I love that slide when you see the difference between the sky glow of, Cheyenne and Flagstaff. Like that's such a great example of protecting your night skies and what it can look like. And again, I would be interested to see if there is any difference in crime. I mean, that's, I get something that would be very interesting to kind of look at. But great slide. I love it. Does anybody else have any other questions?
Mark sent me a question that said, have you seen any studies about how the newer, brighter white car headlights are affecting light pollution? I haven't seen any studies directly related to car headlights. I know they sure as heck blind me when I'm driving, but I'm not sure, yeah, if there's been a direct study on that. You know, they're I know they're a horizontal source of light, but there's still plenty of that's leaking up into the sky. And you would imagine it would have to be a contributor in some way, but at least I have not seen any particular studies yet.
Yeah, I haven't seen anything either. And really, the main focus is going to be those lights that are left on all night long,
Mhm.
and what we can do to improve those, whether it's something as basic as shielding, changing the spectrum of the light, a motion sensor so it's only on when it needs to be, things like that. Um, yeah, that's about.
Any other questions?
One question here. What was used to take those photographs of Flagstaff and Cheyenne from, similar distances?
Oh, if you can actually look down at the bottom of that graphic, you'll
I'm
see
I'm tr
the
I'm trying to squint.
it's the U.S. National Park Service Night Skies program, and you'll notice the dates in the upper right. These were taken in
16.
2016. If you go to the National Park website, I think it's nps.org. Don't quote me on that. Just do a Google search. They actually have a little section on dark skies, and this was a very special setup. If you look very closely at those images, you'll see it's almost kind of pixelated. They took images of the entire night sky, but in chunks, and in the processing of those images, they put them together so you could measure the sky glow relative to other locations in the sky. And you'll find information on that there. The National Park Service. They also have an interactive map, which I have lost myself on quite a bit. And they do this at national parks. So you can see the progress of light pollution, say in Yosemite um, or Yellowstone or things like that. So I would strongly encourage you to investigate there. Um, it was essentially uh, a CCD device, so a digital camera with a lens on it, and they just programmed it to scroll through the night sky, and it took a couple of hours. And they tried to make it as portable as possible so that they could go from uh, park to park. But yeah, the details will be there.
Okay. I was just wondering if we could do a comparison shot,
Mm.
doing something similar at Cedar Creek or at John Bryant State Parks or Hocking Hills, or Lake Hope, any of the parks around here, to see, because as Tracy pointed out, that is a awesome graphic to
Mhm.
convey where somebody's paying attention versus where somebody's not paying attention to the issue. So, okay, thank you.